Welcome to the unit on the binomial expansion, review exercises. The objectives for this session are to use combinations and factorial notation, use the binomial expansion to expand brackets, and convert an expression with linear factors in the denominator into partial fractions. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. We are going to consider the expansion of a plus b to the power n. But before we do that, let's take a look at some factorial notation. Recall that the number of ways of choosing r items from a group of n items is n choose r equals n factorial over r factorial times n minus r factorial, where n factorial equals n times n minus 1 times all the way down to times 3 times 2 times 1, and 0 factorial equals 1. The binomial expansion is a rule that helps expand brackets. The binomial expansion is given by the expression shown on the right-hand side of your screen for a natural number n. We can understand this by considering the expansion of a plus b to the power 4. This is of course a plus b multiplied by itself 4 times as shown. In order to find the b squared term, you can choose multiples of b from 2 different brackets. This can be done in 4 choose 2 ways, as shown. And this is of course equal to 6 ways. Therefore, the b squared term is 6a squared b squared. We will now apply the binomial theorem to an example. Use the binomial theorem to find the expansion of 2 minus 3x, all raised to the power 4. Let's plug in the various values. Here's a equals 2 and b equals minus 3x. N equals 4 and r equals 1, 2 and 3 as shown. Then tidying up gives us 16 minus 96x plus 216x squared minus 216x cubed plus 81 times x to the power 4. Now let's have a look at another example. Find the first 4 terms in the binomial expansion of 8 minus 0.5x, all raised to the power 7. Again, let's substitute the various values into the formula for the binomial expansion. A equals 8, b equals minus 0.5x, n equals 7, and r goes from 1 all the way up to 6 inclusive. However, as we're only interested in the first 4 terms, we're going to look at r equals 1, 2 and 3. So tidying up gives us as shown. Now let's take a look at the next exercise. We are required to write down the first 4 terms in ascending powers of x of the binomial expansion of 1 plus qx all raised to the power 10, where q is a non-zero constant. So let's solve this. We're going to look at the first four terms of 1 plus qx all raised to the power 10. Here's the first term, the constant, 1 to the power 10. Here's the x term. We've simply substituted the values into the formula for the general term. And again, the x squared term, the x cubed term, and the x to the fourth term. Notice that here n is equal to 10 and r is increasing progressively from 1 all the way up to 4. And now tidying up, we have 1 plus the x term plus the x squared term, the x cubed term, and the x to the power 4 term. And then tidying up some more, we have the first four terms in ascending powers of x of the binomial expansion of 1 plus qx all raised to the power 10 as required. Now let's have a go at the next exercise. We are required to find the coefficient of x cubed in the binomial expansion of 3 plus x times 2 minus 5x to the power 6. So let's solve this. Now the first four terms of 2 minus 5x all raised to the power 6 are given on your screen. We have a equals 2 here. We've simply plugged this in into the general term of for the formula. And b equals minus 5x here. Again, we've simply plugged in. N equals 6 here. And the various values of r here. And then tidying up gives us 2 to the 6 plus the x term plus the x squared term plus the x cubed term, and so on. And then tidying up some more, we have 64 minus 960x plus 6,000x squared minus 20,000x cubed, and so on. Now we can expand 3 plus x times 2 minus 5x to the power 6 in order to find the x cubed term for the entire expression. So let's expand this. We only require the first four terms in the expansion of 2 minus 5x to the power 6. And we'll explain why in a moment, because notice we're multiplying by 3 plus x. There are two ways of making the x cubed term in this expression. Either we multiply the constant by the x cubed term, or we multiply the x term in 3 plus x by the x squared term in the expansion. The constant times the x cubed term is 3 times minus 20,000 x cubed, and the x term times the x squared term is x times 6,000 x squared. So putting those together gives us that the x cubed term is 3 times minus 20,000 x cubed plus x times 6,000 x squared, giving us minus 54,000 x cubed. So the coefficient of x cubed in the binomial expansion of 3 plus x times 2 minus 5x to the power 6 is minus 54,000. As shown. Before we go on to the next exercise, let's take a look at some theory. We're going to take a look at partial fractions. A single fraction with two distinct linear factors in the denominator can be split into two fractions. This process is called splitting into partial fractions. So for example, 3 over x plus 7 times x minus 5 is identical to a over x plus 7 plus b over x minus 5, where a and b are constants which can be found. So in other words, we've rewritten the left-hand side as a sum of partial fractions. There are two methods of finding constants a and b, either substitution or equating coefficients. Now let's take a look at our exercise. We are required to split the fractions shown on the right-hand side of your screen into partial fractions by substitution and equating coefficients. So let's solve this. We let the expression equal or be identical to a over x plus 3 plus b over x minus 2. We then add the fractions on the right-hand side by putting them over a common denominator, as shown. Therefore, we now have that the numerator on the left-hand side is identical to the numerator on the right-hand side. If we let x equal 2, and we do this in order to get rid of the a term, we obtain 5 times 3 on the left-hand side, and a times 0, this was what we were trying to do, get rid of the a. So a times 0 plus b times 5 on the right-hand side. This gives us b equals 3. Now if we let x equal minus 3, we have 5 times minus 2 on the left-hand side, and a times minus 5 on the right, plus b times 0. And of course, this is why we put x equal to minus 3, so that we could get rid of the b and find a. And so tidying up gives us that a equals 2. So we've found the values of a and b. And we can express our fraction as 2 over x plus 3 plus 3 over x minus 2. And now for part B. We are required to split the expression shown on your screen into partial fractions by equating coefficients. So let's express this as a over x plus 3 plus b over x minus 2, as shown. And then, similar to the previous part, we express this as a single numerator over a single denominator. And again, we have a similar expression as previously. Now let's multiply out. So on the left-hand side we have 5x plus 5, and on the right-hand side, if we multiply and tidy up, we have ax plus bx, we've put the x's together, plus 3b minus 2a. We've put the constants together. In other words, a plus b times x plus 3b minus 2a. So equating the coefficients of x, we have 5 equals a plus b, and equating the constant terms, we have 5 equals 3b minus 2a. Here are the coefficients of x, and here are the constant terms. We're going to call these equations 1 and 2. Solving by multiplying the first equation by 3 and then subtracting the second equation gives us 10 equals 5a. And this gives us a equals 2. We can substitute a equals 2 back into equation 1 to give 5 equals 2 plus b. And rearranging this gives us that b equals 3. So a equals 2 and b equals 3. When plugged in, give us that our fraction is equal to the partial fractions 2 over x plus 3 plus 3 over x minus 2. Again, before going on to the next exercise, let's remind ourselves of some theory. A single fraction which has a repeated linear factor in the denominator can be split into 2 or more separate fractions. So, for example, we have this equation here, or this identity. The denominator on the left-hand side contains 3 linear factors, namely x plus 7, x plus 5, and x plus 5. Here, of course, x plus 5 is repeated. On the right-hand side, we have a, b, and c, which are constants which can be found. The expression on the left has been rewritten as the sum of 3 partial fractions. Notice that x plus 7, x plus 5, and x plus 5 all squared are the denominators. Let's now take a look at an example. We are required to split the fraction shown into partial fractions. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We're going to begin by letting this fraction be identical to a over x plus 3 plus b over x plus 4 plus c over x plus 4 all squared. For some constants a, b, and c. Adding these 3 partial fractions together and putting them over one common denominator gives us this expression here. Now, since the denominators are the same, as you can see highlighted in red, we can conclude that the numerators are the same. When x equals minus 4, this is going to allow us to calculate the value of c, because the a term and the b term will disappear. On the left-hand side, we have 2 times 16 plus 19 times minus 4 plus 42 when we plug in x equals minus 4. This is equal to minus 2. And on the right-hand side, when we plug in x equals minus 4, as intended, the a term and the b term will disappear because we're going to multiply each of them by 0. This is what we intended to do, and we're now simply left with c times minus 1. Therefore, the right-hand side is equal to minus c. Since the left-hand side and the right-hand side are equal, we have that c equals 2. When x equals minus 3, on the left-hand side, we have 2 times 9 plus 19 times minus 3 plus 42. And this is equal to 3. And when we plug in x equals minus 3 on the right-hand side, we manage to get rid of the b term and the c term, and this is what we intended to do so that we can find the value of a. So on the right-hand side, we are left with a. Since the left-hand side and the right-hand side are equal, we have that a is equal to 3. So now we have the value of a and the value of c. We only now need to find the value of b. Let's plug in x equal to 0 to simplify our calculations on the left and right-hand side, and also of course plug in a and c in order to find the value of b. So plugging all these in, we have the left-hand side. Of course, the left-hand side doesn't have a, b or c, but we can plug in, of course, x equal to 0. So when we plug in x equals 0, we obtain 2 times 0 plus 19 times 0 plus 42. Giving us that the left-hand side equals 42. When x equals 0, then on the right-hand side, we can plug in a equals 3, c equals 2, and x equals 0 to give us 3 times 16 plus b times 3 times 4 plus 2 times 3. Which once tidied up is equal to 12b plus 54. And so, since the left-hand side and the right-hand side are equal, we have that 12b plus 54 equals 42, giving us that b is equal to minus 1. We can now plug in the values of a, b and c into our original identity. So c equals 2 goes here as shown, a equals 3 goes here as shown, and b equals minus 1 here. We now have our original fraction expressed as partial fractions. This brings us to the end of this session. If you have understood its contents, you should be able to use combinations and factorial notation, use the binomial expansion to expand brackets, and convert an expression with linear factors in the denominator into partial fractions. Thank you very much for listening.